Assalamu alaikum, dear students. Bismillahirrahmanirrahim. Dear students, we are we are in lecture number 11 for Electric Network Analysis course, and today's discussion is about the source-free series RLC circuit theory discussion. So this is topic number 8.3 from your chapter 8, and the topic is source-free series RLC circuit. So this is the circuit here. What we will be doing is we just want to find out the response of this circuit, that how this circuit is going to behave. And because this is a source-free circuit, it means that the main energy that is stored in this circuit is due to the inductor. It's an energy storage device, and the capacitor. It will be storing the energy of 1 upon 2 L I naught square, and the energy stored in this capacitor will be 1 upon 2 C V naught square. So this is definitely going to decay. The energy is going to dissipate in this resistance. All the energy is going to dissipate in this resistance. So whatever energy is there, after some time, after going through some process of diminishing, it will just go dissipated, and it will be just consumed by this resistor. So for these are the steps that are already available in your book. This is a quite detailed derivations, but just for the sake of just having a close touch and a direct feeling, I will just explain these things from my own lecture points. So these are exactly the same steps almost. It's just that I have just done it my own writing, so that I can explain it more closely. It gives you a more closeness and feeling of just explaining the things when you just explain it from something which is you have written yourself. So that is my only purpose, that I have used these things. I hope that if you just are comfortable in understanding the topic directly from the book, then you can just directly open the PDF file of your textbook and go through the steps, and these are exactly almost the same. Very minor differences in the steps, and the main thing is that I will be explaining it very detailed in this. And this thing is, yes, I am just recording it. So last time I had a very mishap in lecture number 9. What happened is that I just paused it due to something, some interruption here at my home, and then when I resumed, this Bandicam screen recording screen, so Bandicam software screen recording software screen just got stuck on the screen, and whatever I am just discussing about the PDF file, and I'm just pointing you, I was just having the PDF file in front of me, but the recording was just done with that Bandicam front screen in front. So later on, some student just pointed out that there is a problem with your video number 9. So I just went back and just when I watched it, so initially there was just everything right, but halfway in the video, I just noticed that this was correct. That there was a mistake on the part of the the software. It was not actually recording what was on the screen. It was rather recording the Bandicam software controlling the screen. So that's how you just did not have any display of the things which were being discussed there. So I just updated that video, and I just cut that portion where I had solved end of the chapter 8.3. So then I just removed it altogether and haven't recorded that again. So if someone of you just find it difficult to solve 8.3 end of the chapter problem for the initial conditions, the last topic we had done was about finding the initial conditions. So I can just show you the solution. Right now my focus is just on explaining this circuit. So this is a series circuit excited by its own energy stored in capacitor and the inductor. So the initial current is I naught in the circuit, and the initial voltage is V naught in the capacitor, across the capacitor. So the main variable which we are going to take here is the current I, which is the inductor current. Obviously this is the current for capacitor also and the resistor also, because this is a series circuit. But we will be capturing the behavior of this whole circuit by just taking the main variable of this current, series current. So if the series current is known, so all the other parameters can easily be found out. For example, this VR is going to be Ri, this is VR here, and you see that this is Ri. And if you just want to find out the inductor voltage, so that can easily be found out by LdI by dt. Capacitor current is already there, that is the series current. But if you want to find out the VC, so it can be just found out from the I, if the behavior of the system is captured by the main variable of the series current. Right, so what we do is from here on is that we apply KVL. Okay, from my last experience I just saw that if I just minimize and maximize it, there are some minimum chances of getting stuck that Bandicam screen, because I have got very afraid of that Bandicam screen is stuck, because that has happened quite a few times. And I had initially I had recorded my lectures all over again just because of that that Bandicam screen. Alright, so this is a very difficult task to record the things second time. It's already difficult for managing the recordings at home, operating from home, and now then if you just have to do it twice, you just can very easily imagine how cumbersome that would be. Alright, so so what we do here is this is a series circuit. I just already have told you this is the current through the inductor and this is the voltage across the capacitor. So we apply KVL here. VR, the voltage across the capacitor, VL, the inductor voltage, and the capacitor voltage, that is VC. So VR is given by Ri, VL is given by LdI by dt, and IC is equal to the integration of the I. So we will be taking it as I naught. What is this? Oh, sorry, this is V naught. That means that this is the initial voltage. So if we just take it for time here, minus infinity to t is equal to 0. So this is minus infinity to t is equal to 0. So the result of this whole thing will be V naught. So I hope that you understand this. So if you don't, then you please make sure that you understand this point. That if I just integrate the current through the capacitor from time equal to minus infinity to time t is equal to 0, so what I will be getting is the voltage across the initial voltage across the capacitor at the time t is equal to 0. So we are going to use this fact just in a step ahead. So please be very clear that you understand this point, what I have just explained it. That what is this V0? V0 is the integral, this whole integral provide with the limits of minus infinity here and t is equal to 0 here. Okay, to eliminate the integral we differentiate it. So this becomes this term becomes LdI to second derivative Ld2I by dt square, and this R becomes I is there, this is the main variable, so R di by dt, and this integral will be eliminated due to the differentiation, so it will become I upon C. So just a small algebraic steps of just dividing the whole equation with L. So this L goes out, cuts out from denominator and numerator, and L comes here in the numerator. So to solve the second order differential equation, we need two initial conditions. So we need two initial conditions. So we already have done how to find out the initial condition is the last topics, and we also have done some practice for it. So you just do it if you haven't done it before this lecture. So equation 1, this is the equation 1, this whole thing, this is the equation 1. So what we will be doing is that we will just apply the initial condition at time t is equal to 0. So we want to find out time t is equal to 0. So what will happen is that the I0 will become I bracket 0, that is I at time t is equal to 0, and that is the initial condition, so it will become I naught here. So this is I naught, and then again putting the value of I in this equation number 1, this, so LDI. So we want to find out the derivative of the current at time t is equal to 0. That's why this is 0, is just showing that thing. We just want to find out, and because we are already have put the time t is equal to 0, that means this whole integral is going to be replaced with the initial voltage across the capacitor. So this is V naught, and then what we do is then we just rearrange the terms, and LDI by 0 upon dt we just brought it on the left side of the equation, and then all the remaining variables on the right, and also have divided that by this L here. So this things becomes this thing. Alright, so this is going to be a very important equation from circuit solving and the problem solving point of view. So this is very important equation. You must understand that, you must remember this. So right, so through this equation we will be able to find out the constants A1 and A2. Alright, so this is the second page of this same derivation. I am afraid that I already have taken quite of time for this 11 minutes I already have passed, so I should go a bit faster, or I will have to just break this discussion in 2 lectures. Alright, so again this is the main screen which I am afraid of. If it gets stuck, the whole effort of just explaining and the recording just goes in vain. Okay, so what I do is I minimize it specifically for the reason that that black screen goes away. Alright, so this is the second page of that derivation with the 2 initial conditions I naught, and this is available right from the beginning. This is the initial inductor current, and this we have found out just in the last step. So with we can solve the second order differential equation. From our knowledge of the first order the circuits, we assume that the solution is of the exponential decay. So we are just assuming the solution, what is going to be the shape of the current. So from our initial knowledge of first order circuits, we know that this initial current is going to be decaying in the exponential decay, in the form of exponential decay. Alright, so we are just assuming this thing, and now we will just apply a few steps for solving the differential equation. This is a completely differential equation solving is a complete different subject, separate subject in its own. So I hope that I guess that you already have taken the differential equation course in your last semester. If you not, then this will not be clear enough, but even then we have to go with it. So what we do here is that we put the assumed solution in the equation. I was the main variable of the system, so instead of this, in place of this I have just put this the assumed solution. So this will become this I will be replaced with this A e raised to the power S st. So right, so moving forward and just taking out the common, we just come out with this bracket part of the equation, and this is called the characteristic equation. This is called the characteristic equation of the differential equation. So the main step in finding out the solution of a differential equation is that we have to find out the roots of this differential characteristic equation. So because A multiply e raised to the power st is the assumed solution, it just can't be 0. So the only thing that can be 0 is in this equation. So we will just equate this characteristic part equation equal to 0 just to find out the solution. This is a quadratic equation, it can be easily seen. So the quadratic equation formula is this, that you have to find out the roots s1 and s2 with the plus here and a minus here, and the same things here on both the sides. Right, so I'm afraid that I have just missed out one 2 here. This is 2, this should be 2 here. Okay, so just I beg your pardon for this, you just include 2 here. Okay, so now we just equate this bracket part here, because this is coming here and this is also coming here, so we just equate it to alpha, and then we just equate this 1 upon LC and the root equal to omega, so omega naught, right? So because this is a root, so it will become root square, it is in the root, so omega is equal to 1 upon root LC, so for 1 upon LC it will be omega square, so it is minus alpha plus minus under root alpha square minus omega square. So going further, in the next page, that is the third page of this derivation, so the roots are already found, and I1 and I2 is going to be equal to the S1 and S2, which we found out the roots of the equation of the characteristic equation. The characteristic equation was in terms of the S, and we found out the roots. That means the value of S is found, and because it was quadratic equation, that means there are two roots, S1 and S2. So the complete solution is given by this A1 into e raised to the power minus S1t plus A2 e raised to the power S2t. Both the roots have been included, and constants have been included in this solution. So the main solution, the main step of solving this equation is to find out the A1 and A2. So looking at alpha and omega, so there can be three possibilities. I already have told you that what is alpha and omega in the quadratic equation roots. This is alpha here, this thing, this thing, and 1 upon LC is omega square, omega naught is square, right? So this is called damping factor. Omega alpha is called the damping factor, and this is called the frequency, undamped frequency, right? So going again, so there are three possibilities, that is alpha is greater than omega. So in this case of alpha greater than omega, so the things which are in omega square minus omega square, omega naught square, will be a positive thing, and it will definitely be less than alpha, because it's under root and omega is being subtracted from alpha. I just show you again what I'm just talking about. So right, so if omega is equal to less than alpha, so it will become minus alpha plus minus a positive number, and in the root, and a positive number is less than alpha. So in that way, the S1 and the S2, the two roots, are going to be negative because of this negative, right? And they will be real, because there's no iota here. This thing is big, this thing is small, so it is going to be a positive number under the root, and thus there is not going to be any iota, right? So this is not going to be complex number, so it will be a real number, right, in this case. And the second case is when the alpha is equal to omega. So in that case, when alpha becomes omega, so what will happen, the root will just cancel out, and there will be nothing. So this plus minus will make no difference, it will be plus minus 0. So this will be only alpha, the root will be minus alpha. So there will be just one root in critical damping, so we will have to see it from that point of view. And then there is also a possibility of alpha less than omega naught. In that case, there will be a minus sign and under root, and that will make a iota, so that will make it a complex number. So these are the possibilities here. I was just showing you here that this is overdamped, alpha is greater than omega naught, and in that case C is going to be greater than 4L upon R square. Right, so these are the three possible systems. Either that system is overdamped, critical damped, or underdamped. So we will just discussing it in the next chapter, because I already have reached 19 points, and I have set a limit of the lecture up to 20 minutes. So please watch this video carefully, and also try to see the same topic from the book, and take a good understanding, and then start solving the problem after this topic, that is practice problems 8.3 and 8.4. So I'll be just doing it in the next lecture, inshallah. Okay, bye for now. Assalamu alaikum.